Cool. So today we'll be discussing the paper Successor Representations. It's computational logic and neural substrates. So this paper is basically a review paper on successor representations and the neural evidence in the brain that the brain might be doing something similar. Yeah, feel free to pitch in, keep correcting me if I say something wrong. Yeah. By the end of this presentation, I hope that you'll understand the following things. What is a successor representation and why does it matter? You'll learn some interesting properties of the successor representation, some anatomical details of where the brain might be encoding the successor representation, and what evidence do we have to suggest that the brain is doing something like successor representation. And over time, I would like if you could also form an opinion on the quality of evidence and make a personal judgment on does it even make sense to think about the brain like this, or is the brain doing something very different? So this is the flow of the presentation. We'll look at the big picture and the questions that we are trying to answer with this research. Then we go into some basic reinforcement learning so that all of us are on the same page. And then the idea of successor representations in reinforcement learning, basic idea, how do we learn them, and some intuitions of them. And evidence for successor representations in the brain. Specifically, we look at 3 specific behavioral experiments and 3 specific neural experiments to see how the brain is encoding these things and some future directions. So the big picture. So these are some interesting questions that we as scientists would like to answer. How do the animals represent the world? In RL terms, it would be, how would you want to encode your environment as your state space? And another question is, once you encode your environment, how would you learn? What kind of algorithms would you apply on top of this representation to learn? And we will hopefully make some partial progress on these questions as we go along the slides. So let's briefly cover basics of RL before we try to tackle the big questions. How many of you haven't seen this loop before? Okay, I'll be going fairly quickly through the section because this is basic RL and I'm sure many people are kind of frustrated with seeing this again and again. So reinforcement learning is a class of problems where you directly interact with the environment, unlike supervised learning or unsupervised learning. And generally, the goal in reinforcement learning is to predict or maximize the long-term rewards. And this is the typical RL loop. Your agent takes actions and it gets back reward from the environment. And the entire environment can be specified by just these 2 probability distributions. And it is your transition distribution and the reward distribution. And so in this presentation, we are going to focus more on the prediction part because it's easier to think and analyze that. And when we want to do prediction, what we are mainly concerned with is the value function. So value function specifies the expected return that you would get if you follow a specific policy. I'm kind of going fairly fast through this slide, so please feel free to interrupt me if something isn't that clear. And Q values is pretty much the same as value functions, except that you get to choose whatever you want to do in your first time step, and for the remaining time you follow the same policy. And there are different ways to model this value function that we want, to estimate the value function that we want. One is using model-based and one is model-free. So in model-based, what you do is you try to directly estimate the P and R matrices of your environment that we saw earlier and kind of use them to estimate your value function. And in model free, you don't do modeling of P and R, but you try to find the value function directly. So some algorithms that you use in model based is once you have your P and R matrices constructed from your samples, you use something like value iteration to get the value of your policy. And in model free, you use something like TD learning to find the value. So let's compare model based and model free. And we are going to put successor representation on top after we learn about them on this table so that we are more clear on the good things and bad things about each of them. So let me define a few terms first. Computational efficiency is what I'm defining as the compute needed to choose the next action. We'll go into more detail as I talk about them more specifically. And sample efficiency is the number of samples you would need to learn your value function. If you're in a dynamic environment where your P and R, the environment's dynamics and the reward transition matrix are continuously changing, we would want to relearn very quickly. In that case, we would call an algorithm sample efficient. So let's look at model free and let's think if it's computationally efficient or not. So when we say a model free algorithm, the algorithm would have estimates of Q of S comma A. And it is quite easy to choose your next action. It's basically a lookup table. You can see whichever gives you the most value and choose that. So it is computationally efficient. Yeah?
How do we have that? Like, you need to first compute or learn Q function, right?
That's right. So if we are continuously going through the environment and applying TD learning and learning a value function, then we have Q ready. While in the model-based case, even though we are continuously going in the environment, we have good estimates for P and Q. But if you want to get the Q of S comma A, it takes quite some compute. You have to do the whole value iteration process. If that makes sense. So in that sense, we would say model free is computationally efficient. This kind of relates to what we were talking about, chess. When you look at chess, okay, let's not get into that. We'll be having this debate again. But anyways, and when we look at sample efficiency, model-free methods are not sample efficient because even if a small part of your P or R matrix changes, you'll have to relearn the value functions all across your state space. Whereas in model-based, you can only learn that specific part of the reward or transition distribution. In that sense, it is model-based is sample efficient, whereas model-free is not. Okay. So end of background. Let's get to the core, successor representations. So an interesting way to think about the successor representation is that it is an alternative to find the value instead of using the Bellman equation. So this is very loosely the Bellman equation. I mean, I don't have the expectation and all, but I tried to use notation quite loosely so that the idea is more concrete. So this is generally how the Bellman equation looks like, and we can reorganize this equation to write it in this specific way. We can put all the rewards in one matrix and put all the coefficients in another matrix. And this is essentially how the successor representation is doing it. So looking at a specific example of a linear chain where you start here and then you transition and then you have a terminal state, this is how your M matrix would look like. So the first row represents the V of, so let's say we are looking at this state, What M essentially encodes is the future state occupancy matrix. What do I mean by that? So when you start here, you would likely be in this state for one time step, and you would be in this state for one time step, and you would be in this state for one time step. And if we do discounting, you would be in this state for one time step, you would be in this in this state for gamma time steps, and this state for gamma square time steps. So this is essentially encoding your future trajectory. So if you're starting at this state, this row represents the probability of, it's not exactly probability, but the expected future time you'll spend in each state. So if you start here, you spend one time step here, gamma time steps here, and gamma square time steps here.
That's not an integer, right?
That's not an integer.
How can we spend like gamma or gamma square time steps?
So
I think it's just some kind of weighting or like weighted matrix kind of thing.
So when I say time steps, I'm also talking about time steps in expected sense. So if you kind of understand gamma as the probability that your agent would die after one time steps, the expected time that you would spend here would be gamma, because you die with 1 minus gamma. Yeah. Yeah.
So if I understand correctly, the future occupancy matrix is like a probability.
Can you speak a little slowly? I'm sorry.
If I understand correctly, the probability, the future state occupancy matrix is like a probability distribution over future states.
That's right.
So, then do you need to like bound it somehow, like a maximum number of time steps, or like how do you define like the I guess the bounds of this?
So right now we're looking at just an episodic case. So the episode terminates at some place.
Okay.
So so your question is, how do we ensure that the value is bounded? Is it?
My question is, how far do you look at the future? Basically?
How far do you look into the future? So ideally we would want to look as far as possible. In this formulation, we look as far as possible. Yeah.
I think because there's discounting, the value just decays, so it makes it profitable. You're not looking at all possible into the futures because we're discounting states.
So it's not like whenever.
Yeah, that's right.
So it's not like whenever you have like.
Yeah, I guess like those on that point, I guess like the field is all that. I think.
Yeah.
You were the experts.
I'm not the expert. So yeah, essentially, if you get +1 here, +2 here, and +4 here, we're kind of reweighing the rewards based on how late we get them. So this is intuitively what the SR is doing. If you have any more questions, or if someone wants to say something about SRs to make it more clear, please go ahead. Yeah.
So, if I understand it correctly, were you just basically rewriting the, I think the dominant region? So all the reward comes up, and then the discounting and the state occupancies is
Right.
out of the building. I don't know, compiled.
Yeah, compiled. Yeah, that's perfect.
Okay.
Yeah, we are decomposing the rewards and the future state occupancy separately into two different variables. So the advantage of doing this is we can learn M and R separately. So if you have some changes in your reward structure of the environment, you don't need to relearn your M matrix again. And if there's some change in M, you don't need to relearn R. So you have two different learning parameters for two independent learning parameters for both reward and transitions.
How many parameters is there in M? Is it just one?
So M is a matrix that looks like this. If you have 4 states, it's S by S.
But if you're just learning, like the only thing you need to learn if the transition in states is fixed, then the possibility of transition is just the gamma.
Say that again. So
what are you learning in this one?
So I think here we are not learning anything. We should be trying to learn value function.
Yeah. You said that you.
yeah, so ultimately we want to estimate the value function, and for estimating the value function we'll have to learn R and M. And how do we learn M is on the next slide. Maybe then you can.
So we only learn gamma then.
We learn M and R, we don't learn gamma. Gamma is.
So M is this matrix which is fixed, right?
It depends on the policy.
That's right.
So does R in this case. So both those depend on the policy.
But what exactly are the parameters we are learning here then? Because R is something which comes from the environment.
But there's also the action. I was trying to think because there's no action there. So that it's, I guess, is it the reward when you're in state S prime and you take action A according to the policy? So there's like a hidden policy parameter there.
So yeah, I should have been clear about that. We have a fixed policy here. We're only talking about the prediction case. So when we start off, we would initialize this as a random matrix and this as a random matrix. And as we keep interacting with the environment, we want to get more and more accurate estimates for M pi. So what you would actually learn is all these numbers in your matrix. That makes things clear. So M is called the successor representation because it shows you the probability that you will be in a successor state. It's not probability, but expected time steps you would spend in a future state. And M can be thought of as a compact representation of P. So P is our transition matrix. And in the case of a linear chain, P would look like this. Because if you're in state S0, you have a probability of 1 to transition to S1 and 0 everywhere else. And if you're in S1, you have a probability 1 to transition into S2 and so on. So M pi is kind of compiling the information of your environment into another matrix. And here, for the linear chain case, this is how they would look. And one thing about M is when you move from your P space to M space, you lose out on information because M is not encoding the order in which you would reach the states. So this M is only telling you that if you start here, you will spend 1 time step here, gamma time step here, and gamma square time steps here, but it is not telling you in which order. So multiple P's can map onto the same M, and that is how in model-based we try to estimate this, whereas in the successor representation we're trying to learn this. And how do we learn the successor representation? So I'm not going into all the math of this because I wanted to spend more time on the experimental evidence, but basically you will have a temporal difference style learning algorithm to learn the successor representation, where the error signal is the discrepancy between observed and expected state occupancies. So the thing that I want you to take from here is that it learns using a TD style rule. And in this TD style rule, your error is a vector. So in traditional TD, your error is a scalar. When you're trying to estimate the value, your reward prediction error is a scalar. But here you have a vector. I'm intentionally skipping out on the math of how we get here. Maybe if we have time at the end, we can go into more of this math. Where does successor representation fall in on that spectrum? So model-based is very flexible but low efficient, and model-free is high efficient and low flexibility, as we've seen before. And successor representation falls somewhere in between. Why? It's because in the successor representation, you're trying to learn P and R separately. So if just your R changes in the environment, you can still adapt quite quickly because you already have your P learned. So in that sense, it's still flexible, and it is also efficient in the sense that by reformulating the successor representation, you can also estimate M of S comma S dash comma A, and this can help you estimate the Q of S comma A. So you can continue to implement your lookup table. So we'll go into the neuroanatomical details next, but if you have something to add or something to ask, you can. Okay. So neuroanatomical details, I'm glad. Are there any neuroscientists here? Oh God. Oh God. Okay. I'll try to get away saying a few words about all this stuff. But yeah, feel free to correct me if I say something weird. So cognitive map is a concept, I think, which comes from the neuroscience field, where it is the idea that how do we represent our environment inside our heads? That is what we call as the cognitive map. And traditionally, place cells in the hippocampus, which is somewhere around here, is thought to encode environment inside our heads. So so the place cells were collectively thought to encode the cognitive map, which is our environment, and the main evidence for it came from one experiment that I'm going to show you a video of soon, in which the pyramidal neurons inside the so a place cell is basically a pyramidal neuron. Maybe I'm using jargon that I shouldn't, but the idea is that this place cell fires whenever your rat is in a specific place in the environment. So people thought, okay, one place cell is firing each time I'm here. Another place cell is firing each time I'm here. Maybe it is kind of encoding the spatial location of the animal. And yeah, when I was first reading about this, I had some questions. What if the place is too large? We don't have infinite number of place cells to encode all of space. The idea is that place cells are reused. One place cell is here, and once you go far out, another location is encoded by the same place cell.
So you'd target the old location?
No, it would fire both here and somewhere else, is my understanding. Please correct me if, yeah.
So where does the notion of like grid cells come in here? Are they different?
I don't understand grid cells very well. If anyone understands grid cells stuff.
So what was the question about the grid cells?
So how does grid cells fall into this picture?
From what I recall, basically grid cells it fires if you are at so it's not like absolute distance, but rather it's like relative distance. So a grid cell will fire if there is like a relative position with respect to like something.
So it kind of fires it with a grid. So it's like so you can use multiple different spatial representations.
So they also kind of do this like location business, right? But they're not really related to place cells.
They are related, but if you think of place cells as like encoding a specific place, and the grid cell is encoding, like relative in the sense that as you're moving, the same grid cell might fire.
So like if you put it on a map, A place cell would be like a single place, whereas a grid cell would be a grid.
Yeah, something.
What do you think? I'm not sure.
Yeah, I think that makes sense. And what if we move into a different environment? Do we have new place cells to encode just that specific environment? The thing is no. You reuse the same place cells even if you're in a different environment. So let's. Okay, we've discussed what successor representation is, but how can we actually test if the brain is doing successor representation? This is an interesting experiment that we can use to test that out. So the old belief was that each of these place cells encodes the present location. The successor representation hypothesis is that each cell doesn't encode the present location. What it actually encodes is the expected occupancy of a state. So let's think about it for some more time. So if your animal is in this state, the successor representation is going to look like this. So this would have an occupancy of 1, gamma, gamma square, and so on, if it's going along this linear track. And if your rat is in this state, you would have 1 here, gamma here, and then a slow decay there. So the SR hypothesis is that each cell encodes the expected occupancy of a specific state. So a cell would encode the expected occupancy of S phi. So if we look at just S phi, when your agent is in S1, you would have a low firing rate. When your agent is at S2, you'll have slightly higher firing rate. So this is basically the plot. And when you're at S5, you'll have the maximum firing rate. And when you go to S6, it will suddenly drop. If you have, yeah?
So each node is a cell.
So this is a rat running along a straight line. And yeah, we're discretizing the state space into multiple states.
I guess, I mean, like S1 to S5 are neurons or place cells.
No, I think the figure E, just the figure E is the entire representation of one cell at position S5. Correct?
What do you mean by entire representation?
What is encoded in the cell 5 basically? S5.
Okay, so
that's the entire figure E, right?
So what the figure E tells you is when you're at this location on the x-axis, with what frequency would your place cell fire?
The place cell encoding for the location at S5.
That's right. Yeah?
Yeah, I'm just I'm not sure how the plotting peak and how it is you can differentiate between the SR hypothesis or a simple decay function like Gaussian function or some kind of resolution on the location that you think you have.
So maybe like if it's just decay functions, when you're in S5, S4 should be higher than what is there in this equation.
So you think that the sensitivity to the location is too high to be a simple.
Just not symmetric. That's right. So
Yeah.
So if you're in S4, S5 like very likely next step. But if you're in S5, S4 is not likely. So it's not symmetric. If it was just like, I mean, I'm just looking at the graph. I don't know if it's this one. Maybe that's the way to see this.
Yeah, so the idea is if you had a traditional old belief, which is, maybe I shouldn't be saying that, but if you have the traditional thing that it encodes just the location, then what you would see is a symmetric curve around S5. But because of the SR hypothesis, we have a sudden dip.
Okay, because you know that the mouse.
Yeah, because the mouse is moving towards the right. So once you go to S6, the expected occupancy of S5 is kind of 0. That makes sense. You have a question? Yeah.
Because here the expected occupancy of S4 is not 0.
Uh,
So how would the expected occupancy of S5 be 0 if it moves to S6?
so look at this plot. When we are at S5, the expected occupancy of S4 is 0. I mean, ignore the small height. So when you're at S5, it is 0 and you have the decay forward. Your gamma decay is here.
But then why is figure E different?
So,
I think figure.
Sorry?
Well, notice on the y-axis it's like MS, some symbol SI or whatever, S5, and on those it's wherever the rat is and then the SI.
So
SI
in-
is like
yeah.
x-axis.
in one case, we are plotting the row, and in the other case, we are plotting the column of the M matrix.
So interpretation of figure E is the firing rate of S5 given where the mouse is.
That's right. So yeah, this is one way to test it, and we'll go into a specific experiment to see if this is true, but I just wanted to give a feel of how these experiments will be. Okay, let's get into 3 behavioral experiments and 3 neural experiments. So this is an experiment from 1930 where rats, so this is the learning curve when your rat always gets a reward, and this is your learning curve when your rat is allowed to explore in an unsupervised way, and then you start to get a reward. So here what this is suggesting is you're also doing unsupervised learning in the environment when you have no reward. So that is the behavioral evidence we see here. And because of that, we can say that we are not the rat is not using just a model-based method, because model-based methods cannot learn if you don't have a reward. So this is a reason to believe that it's either doing model-based or successor representation. Yeah.
What if it gives itself intrinsic reward from like satisfying its satisfaction of seeing new environments or something? It'd still be learning like that, but with some kind of self-given reward based on exploration or something.
So if it is getting self-reward, how would you explain the sudden learning as soon as you see a reward?
I don't really know what
Okay.
the like task is.
Oh, okay. But yeah, maybe we can talk about it after. Yeah, but the basic idea is that rats are learning even when there is no reward. So it is in line with model-based and successor representation, and probably some of your hypothesis too. And then another experiment where the rat is continuously trained on 2 different tasks. Task number 1 is whenever it pulls a lever, it gets sugar. And task number 2 is it is given sugar and it becomes sick. And this is probably done a few tens of times, and this is again done a few tens of times. And turns out that the rat learns to associate the level of sickness to the lever. So when you put it back in the environment, it doesn't press the lever anymore, because it associates that it would give you sugar and that would give you sickness. So what we see here is it's able to generalize across these trials. If we were using a value-based method, so here we would associate the value of 1 to the lever also. And in this case, we would reduce the value of sugar based on these trials. but you don't update the lever anymore. So if you're using a value-based method, this has to keep happening. It should be continuing to press the lever, but it doesn't.
Can you explain that again? Why should it be pressing lever if it's value based?
So do you understand why it doesn't press if? Did I say it has to press if it's value-based?
It shouldn't. I think you said it shouldn't. I don't know.
Okay, I'll just reframe. I'm sorry. So if it is value based, you tell me, should it press or should it not press?
I don't exactly understand the relationship.
Okay, so let's say we're using a value based method, and we continuously have this trial.
Yeah.
So the value of your lever would become +1.
No, because the episode doesn't end right there, right?
So this is one trial. This is all that happens in the trial. The episode ends there.
Okay, but like experimentally, how can you say that it ends there? Because it further leads to sickness.
Okay, I need some neuroscientists here. Okay. So when you're doing the first experiment, sugar doesn't lead to sickness at all. Okay. When you're doing the first trial.
Okay, when does sugar lead to sickness then?
So you do this trial tens of times.
Okay.
And you don't get sick when you have sugar. And then you have this new trial that you keep doing repeatedly, where it is given sugar and it gets sick.
I'm just trying to understand the high level idea of this experiment. So basically, if I understand correctly, the fact that you see that the rat learns to avoid sugar because he expects that sugar will lead to sickness, it shows that the rat has to take into account some future events and not just the immediate event that's going to occur after the
Yeah.
Wait, sorry. So what was the debate?
So I think it just learns that for value based it doesn't necessarily learn, but if it's like successor feature based, then it learns that it shouldn't take sugar because it ultimately leads to sickness. So it's some evidence that the successor representation learning is happening.
I was going to ask about model-based view.
Yeah. So again, this data can again be explained by model-based and successor representation. So I think this successor representation in the brain is a very recent idea. People used all these experiments previously saying it's model-based, but turns out SR can also explain all the data that we observe. So yeah, recently there was a specific test done to find out just that, to differentiate between a successor representation and a model-based thing. So humans are given this task where so how do we differentiate between a model-based and successor-based system? So successor-based system is very flexible to changes in rewards. If you change a reward, it can still learn in one shot. Whereas if you have a model-based system, if you change, it's robust to both reward changes and transition changes also. So even if you change the transitions, it can quickly adapt. Whereas the successor representation cannot. So one way to test it out is have an environment where you try to change the reward transitions a bit, see how the learning progresses, try to change the model dynamics a bit, see how the learning happens. And if both of them are fast, it suggests model-based. If reward is fast and model changes are slow, then it suggests successor representation. Yeah.
If you just change the reward, will successor representation be faster than model-based?
It would be equal.
It would be equal.
Oh, so when you say faster, are you talking in terms of computational efficiency?
I guess I mean you just like, maybe this is too overly naive, but I just thought you need less samples because you're just swapping out the reward as opposed to having to.
So so samples, both of them would need the same number of samples. So learning the rewards is kind of the same in both the cases, the SR and model based. What changes is how you're learning the transition dynamics. The SR compresses it into a MPI matrix, whereas the model based system learns it separately. It doesn't compress it into.
So in one, so if you change the,
If we change the reward,
right, then model-based and successor representation learns equally.
yeah,
If you change the dynamics, then model-based learns faster.
that's right.
It doesn't seem to me like you can still differentiate. Like, anyways, sorry.
Yeah. I mean, it's hard to make judgments based on just this behavioral data. We also have some neural data, maybe that would
I'm
convince
just
you.
missing a few like pieces. But maybe if you present the next one, I'll understand better.
Yeah. So, because we have more experiments to cover, I won't be going into the details of this, but based on the behavioral data of how humans adapt to changes in rewards versus changes in transitions, this is what they conclude. They say that successor representation provides an initial estimate and then it is refined by model-based computation. So it is some kind of interaction between the model-based and successor representation that would explain the behavioral data that we observe. Okay, so people who haven't seen this before, I think this is going to look pretty cool. This is just a place cells experiment. When you're recording from one cell, when a rat is moving around. I hope this runs. What happened? So the rat is moving around the environment. The dots you see is the recording from a place cell. So each dot represents its firing. So the rat is moving around with a random policy right now. It doesn't have a reward anywhere, so it's just exploring. So once you average it out, it kind of looks like this. And yeah, this was the initial place cell experiment where I think which helped people say that it is kind of encoding place. But yeah, the authors here argue that it also explains successor representation. So for a random policy, when a rat is navigating around, the successor representation resembles what we see in the place cells. But so would be the case even if it was just even if the place cells were encoding just location. So we still can't say anything for certain. So we need to up our game, come up with more advanced experiments to test this out more clearly. And yeah, I found this quite cool. And I would love to see more videos like this when neuroscientists do behavioral experiments. Yeah. So experiment number 2. This is the same task that we've seen before. A rat running along a trajectory from left to right. So this is what we would expect ideally in simulation if the brain were doing successor representation. And when we actually record from the brain, this is what we see. I mean, it's still not a perfect drop, but it kind of has this bias towards the left. So this data seems like it explains. So this data explains successor representations more than a model-based system. So if you're doing a model-based system and just encoding the place cells, you would see a symmetric curve here, as we've discussed before. But you see this leftward skewing, which means that it might be doing successor representation. And another experiment is place cells tend to cluster around the rewards that you see in your environment. And this is again explained by successor representation and not model based. And yeah, there were a few more experiments that were quoted in the paper. So when you add barriers in the environment, the experimental evidence suggests that the distortion in place fields you see is consistent with the SR hypothesis. And something with lesioning out some part of your hippocampus and some brain imaging studies in humans seem to be all inconsistent with the evidence we have seen. But we have one big issue here, which is we need a vector valued learning function for the SR, as we discussed. But the traditional way, the traditional view of how we learn the value function is through the reward prediction error that comes from dopamine. And the traditional view is that the dopamine encodes a scalar. Okay, maybe I should give you a little more context here. So dopamine neurons in the brain, I think they're somewhere in the midbrain, are believed to encode the reward prediction error, which is used to learn your values. So when you're doing the value update, you have a reward prediction error term. It is believed that these dopamine neurons' firing rate encode that parameter. So yeah, I mean, if they're firing and you look at the firing rate, it seems like a scalar. So how can an SR be learned? Because it needs a vector to learn. They quote this paper saying that it argues that phasic firing of midbrain dopamine neurons do provide necessary error signal to learn the SR. But I didn't go into that paper, so I'm not going into more detail here. Any questions before we?
2 slides back, why was this an example of SR and not?
This one?
I think there's the next step, this one.
This one?
Yeah, the centering around rewards. Why is that not model free or model based?
So if you have a lot of rewards in a specific part in your environment, multiple. So let's say a place cell is. Okay, I'm finding it hard to explain. I'm actually getting a little confused. I did think about this, but.
Wait, so I don't have an answer. I guess think about it too. So if it's model free, then whatever your reward is, that place cell.
So what we are essentially trying to figure out is how we are encoding the state space. So if we are encoding it in the traditional way of place cells, then you would see a uniform distribution of all your cells. But if you are encoding it in the SR way, where you are taking the predictive representation of
predicts your paths take you closer to the rewards, but model-free policies, or sorry, model-based policies would take you closer to the reward, I guess.
So when I'm thinking about model-based and model-free, what I'm thinking is how you encode the state space is just S. But when we are doing SRs, how we encode the state space is not directly S, it's the predictive representation. Yeah?
Yeah, I just wanted to comment. I kind of agree that this experiment is not, for me, it's not very strong evidence for Econ. I think by far the strongest evidence is in experiment too. Why? Because this can be explained by neuroplasticity, right?
Explained by what?
Neuroplasticity.
Okay.
So it's the idea that the regions that get used more often tend to have more important connections in the brain. Because that rewards to expect the rat to go more often in the region which rewards, right? This can explain the decision.
Yeah, that makes sense.
But the second experiment, on the other hand, I think is quite interesting because it does seem, at least from my limited understanding of RN, to exclude the other candidates, right?
What was the second experiment?
The one where you see the asymmetry, that is the architecture of the.
So did you look into the place source are more clustered around the reward paper?
Just.
So it's just from this sentence? Like in the instant Gershman.
I mean, I just skimmed. He has another paper, hippocampus as a predictive map. I think I got this part from that paper and some of his slides on YouTube. The screenshot is from his slide on his YouTube video.
I guess I'm also confused whether it's like there's physically more place cells around the reward, or sorry, I guess there are physically more place cells encoding areas around the reward.
Perfect. Yeah.
I guess that's what they.
I would guess.
Yeah, that's right.
More of the given place cells are corresponding places closer to the board. It's like a non-Euclidean map of cells. It's like bubbles up closer to the board. That's my picture.
Oh, I see. But I guess, yeah, like, it's not this particular sentence is not a strong argument, I guess, for successor representation. Because I guess it doesn't say anything about, like, I don't know, number of place cells isn't the same as your M matrix. It's just like I don't know, like the finer resolution of a subset of the matrix in the system.
In the direction of travel experiment, was that experiment with reward as well, or were they just running around and?
So how they train the rats to keep going to the right is they continuously keep giving them a reward here at the end, so that it's trained to go in that direction.
And do they switch sometimes where the reward is?
No. So the intention of the experiment is to train a policy that the rat would keep going right.
Wait. But if you do change the reward in that experiment, the firing shouldn't change.
So in that case, if the rat is not moving towards the right and it is moving with a random policy, then this is what you would expect to see.
Yeah. But I'm saying if you train the rat, so it has now the policy is fixed.
Right.
So then the state transitions are fixed.
Right.
So then if there is SR, then the skew should still be there because the expected future occupancy stays the same even if reward changes because the rat has yet to learn the new rules.
Huh.
Right?
Yeah.
Yeah. I was wondering if you're switching reward.
So maybe we can look at that later on.
Yeah, I mean, in the conclusion, they do suggest a few experiments around this because. So what happens when the rat changes its intention? Let's say it's going here, but it changes its intention and wants to go in another location. Do the place cells immediately remap so that based on its intention, or how does that work out? They were saying we need more experiments to clearly figure out what is going around in that space.
It seems like it would be hard to have a very fast adaptation from all perspectives because then you need to remap the connection, right? For example, I just need to have some adaptation of the strength of these snapshots.
Again, assuming it's SR, it's gonna take a while, like take some trials for the policy to be updated towards the new one. So the directional bias should persist for a while, even if you change your report.
Yeah, yeah.
Because you're only doing value evaluation, you're not doing policy improvement. Maybe we'll look at the future text.
So I spent some time wondering if I should add this slide or not. I asked Blake if he was coming. He said he wasn't. So I could dare to put this slide on. This is kind of intentionally provocative. So again, I'm not saying that this paper makes unreasonable claims. They question the idea just as much, but I believe there are some broader questions about the method of science that are interesting to think about. And as Jess says it, she's another member of the reading group if you don't know her, and she's awesome. So she says that the brain is much more complicated than the stories we like to tell ourselves. The moment she said it, it just stuck in my mind. And yeah, it just keeps coming back to me whenever I'm reading about anything about the brain. And it's easy to fall into the details and lose perspective. And I was just working on this slide last night, and I had questions like the more philosophical questions of the unreasonable effectiveness of math. Why does math explain the universe so well? And would it... So people say that math has been able to explain physics, but maybe it wouldn't be able to explain biology because it's more complicated. And our tools of math are not good enough, maybe. And yeah, I just start to wonder if that would break down. Are we just wasting our time studying these constraint systems? Are we even making progress? Because we're looking at a very specific part of the brain and trying to overfit multiple hypotheses on this very small data. And I know that I don't have an alternative approach. I don't have a better way to go about things. But yeah, it's just frustrating that we are modeling very simple systems to approximate the brain. And yeah, I would like to wrap it up. If you guys have any comments or...
I was kind of thinking the same thing because those